can also do acquisitions of signals on the ground, like if you use a mobile phone or something like this, then this could be seen by Hawkeye 360, and we can also acquire these images and combine this with our other data like radar optical data. And there's more to come, so we're also working on the next generation, like the next generation radar and optical part, and yeah, more to come. This is a quick overview of the different images and the different, yeah, let's say bands we have, and also the techniques, so radar imagery, optical imagery, and all the different acquisition modes. All right, then, yeah, this is just an overview of the different acquisitions we could do and the coverages. So low resolution, DMC constellation coverage. And if we go to higher resolution, typically the footprint decreases, but yeah, with respect to the higher resolution we have. So I will now give a quick overview of the satellite which has been launched last year, the Pléiades Neo, which will, at the end, when all satellites have been launched, a constellation of 4 satellites with 30 centimeter optical resolution available. So that's the first commercial 30 centimeter imagery which is available on the market. There will be also MDA or Maxar who will also launch their satellite most probably within this year. So this is just how the Pléiades Neo looks like. As mentioned already, 2 satellites are up in space, 2 more to come. And we have a location accuracy of 3.5 meters, which is also very precise with respect to optical imagery, the best available, and also with 30 centimeter native resolution, as you can see here in this sample. And additionally to what has been there for Pléiades up to now, Pléiades Neo now also gives the access to new spectral bands. And yeah, as you can see, there's the deep blue, which hasn't been there before, from 400 to 450 nanometers, which gives additional capabilities to acquire images and to extract information based on the optical images. This is just a general overview. We have 4 identical satellites, 30 centimeter resolution, 2 times a day revisit, and we could acquire 2 million square kilometers per day. The satellites are launched and designed for a 10-year lifetime. So we hope that at least 10 years of operations with these satellites, probably even more. If you compare this, for example, to the optical, to the radar satellites, they already extended their lifetime more than 2 times. So there's a good chance that we can also manage to have longer lifetime for these satellites as well. Some sample imagery, and this is a nice sample from a glacier here in the Antarctica. Some nice faults which are visible here in this 30 centimeter image. So I think the precision and the quality of these images really is it's a nice one to do also some classifications based on these images. And another example. There are different applications which you could use here for the optical, for the Pléiades Neo data. Just some examples which I picked here. With the Pléiades Neo 30 centimeter resolution, we have a revolution in the urban mapping because we have very good opportunities to acquire the cities with different incidents, with different looking angles, and also yeah, based on the 4 satellites we have, we can also acquire large areas within short time period. With the deep blue band, there's also an additional use now within the maritime sector, and yeah, I think there will be a lot of applications coming up also with the new data and more possibilities to use the data within this sector. Now let's jump away from the optical and go to the main focus of this presentation, which is more on the radar constellation. As mentioned before, I'm mainly focusing on the radar part, and that's why I want to put my experience in this topic on this talk here to give you an overview of radar imagery, of our radar constellation, and all the applications which are possible with radar imagery, because I think most of you already know the applications based on optical, but probably not that much about the radar imagery, and that's what I want to give you an insight on this. So first of all, we have 3 satellites in our radar constellation, if we do not take the Novasar into account, which is a separate mission. So we have the TerraSAX, TANEMX, and PASS. TerraSAX launched in 2007, TANEMX launched in 2010, and PASS launched in 2018. So you see there's some gap in between the launch of the different satellites. Actually, PASS satellite is launched and operated by our Spanish partner Hisdesat. It's a satellite from the Spanish MOD, and TerraSAX and TANEMX are satellites from the German government. It's a public-private partnership with the German government, represented by the German Aerospace Center, and us, Airbus, as the commercial exploitation partner for the imagery. And we built up this constellation here with the Spanish partner to have a full constellation and more possibilities to acquire images. They're all comparable, so you will not recognize the difference in the images if you just look at them. It's just the naming which is different, and that's it. So you can use them in parallel. The radar constellation, as you can see here, is based on one orbit, which is holding the 3 satellites, TerraSAX and TANEMX flying together in a close formation. We will see the reason for this later on when we talk about the elevation data, and PASS satellite flying some hundreds of kilometers apart from the 2 satellites and acquiring this images also in the same orbit. So if you haven't seen any radar images so far, I will just give you some basics on this. So this is the optical image of the area of Lake Constance, of the city of Constance. So you see some water area, you see some city areas in the center, and some forest and agricultural land in the surrounding. If you compare this with the radar image, you see that it's not nice colorized. It's a grayscale image. The reason for this is that it's an active sensor, and it's also a side-looking system. The data the signals are sent towards the surface and then reflected on the ground. And depending on the roughness of the surface, you get some reflections back towards the sensor, or the signals are reflected away from the sensor. So on a very smooth surface like the water, you see that most of the reflection is reflected away from the sensor. That's the reason why it appears black in the radar image. For the forest area, some reflection gets reflected away from the sensor, some is reflected back towards the sensor. So you have this medium grayscale. And in the built-up area, you see that there's a strong reflection in this area here in the city area, strong reflection at the houses, at the different infrastructure elements, which are reflected back towards the sensor. So these areas appear very bright in my radar image. These are just some basics. Nevertheless, additionally to the amplitude or to the roughness of the surface, which is reflected back to the sensor, we also get information on the phase information. So which part of the wave is reflected on the ground. And this is an important information if we look at the further applications using the radar data and the advantage of using radar data compared to optical images, because you can do some additional interpretations which are not possible with the optical sensor. So the main advantages of radar, first of all, is globally access. You can either access it via your own antenna, or you can use the main site and get your processed data. And we are also independent from the clouds and from the sunlight. So even especially in your region, there's a long period where you have not too much sunlight. I think the sun probably just came 1 or 2 hours ago. So with the radar satellite, you could also acquire images during the night. You can also look through the clouds. You have an active sensor, so you're completely independent from the sunlight. And additionally to the amplitude information, so the reflection on the ground and the intensity, you also get the phase information. And mentioned before that we will also take a look at the applications based on this later on. And we have a very high precision. So the orbit accuracy of the satellites is in the range of 10 centimeters, which allows to calculate XYZ information in the range of up to 10 centimeters on point base. And then we have the radar constellation with a repeat pass of one satellite every 11 days. So every 11 days, the satellite is in the exact same location. If you take all 3 satellites into account for the radar constellation, we can do a repeat pass every 4 and 7 days. So less than a week repetition frequency of the satellites to do a monitoring over a longer period. And yeah, this is a news which has been there on BBC yesterday. Thanks, Benjamin, for the link. And this is just not based on our radar constellation for TerraStar Xdynamics in the past, but for Novastar, which is also partly operated by Airbus. And this shows an image of Great Britain and Ireland acquired with Novastar in some images. And this has been recently launched. And there's a nice statement also in the article mentioning the mosaic is made from imagery acquired by the Novastar satellite. And actually, the important part is down here. A traditional optical satellite which views scenes at wavelengths familiar to our eyes, would struggle to make such a map in a short time. Britain's famous grave weather would be a constant frustration. So this already shows the advantage of radar data compared to optical data, that you could also acquire these images in period with bad weather or during the night or when you have not much sunlight. Okay, going back to our radar constellation, you see that we have different acquisition modes going from low resolution, 40 meters, up to very high resolution, 25 centimeters. But depending on the acquisition mode, we have a different coverage. So large coverage for the low resolution between 200 and 270 kilometers footprint. And for the very high resolution, it's around 4 by 4 kilometers, which can be covered. And you see that depending on the application, the different modes can be selected, and also makes sense to go for the different modes depending on the application. For example, for maritime applications, for monitoring, you typically go for the low resolution because you can still detect objects like ships on the sea using this acquisition mode, but cover a large area. If you want to pinpoint the detail, then you typically go for the staring spotlight with 25 centimeter resolutions in azimuth, and which gives you very precise information on the objects on the ground. There's a variety of applications which could be covered using the radar data. For sure, it also covers applications which are possible to cover with optical data, but there are some additions. And I don't see radar data as a competition to optical data. It's always an addition, and by combining all the data, I think you get the most data out of it, or the most information out of it. So the main application which I mentioned here is the surface movement monitoring or interferometric processing, which is also used for the change detection. We will look at some samples for this. Vessel detection already mentioned before. So based on the reflection you get from the ships, you can easily detect ships even in large areas with low effort, because they are very nicely visible in the radar imagery. Then we can generate XYZ information, very high precision based on the ground control points. And then last but not least, elevation data. So let's quickly run through the different applications, starting with this example. So if you do monitoring over a long period, in this example here, it's the Pine Glacier in the Antarctica, covered in several shots. And you see that over time, you can nicely see the crack of the ice within this area. So this is the first image on the upper right part. And then the big picture is the latest or the last picture acquired in the series. And if you combine these images, you can easily detect the change and the, let's say, the crack of this ice over time. Then this example here is from Iceland. So there was this volcanic eruption in 2010, and we have taken two images and created a stack out of this. One was before the eruption and one was after the eruption. So it was in March and April 2010, these two acquisitions, and the colorized image is the stack based on both images. So that's the advantage of using radar data, based as you have the reflection on the ground and the active sensor always the same, let's say, energy which is sent towards the surface. You also get the same reflectance back. So if you combine the images, you only see the changes within the area over time and not influenced by different sunlight or something like this. And this also shows here in the stack the change which has been there due to the volcanic eruption. And you see, for example, that there has also been a change on the upper left part here in the river flow, but also in the main area of the volcano, you see the different changes. So the different colors represent the changes either with additional material which has been placed there due to the eruption, or some blasts of material away from the surface. So this has been done using the change detection. So change detection with radar, as mentioned before, is pretty nice because you only see the changes which are there based on the difference in the reflection due to changes on the ground, or in difference of the phase information. So additional to the reflection, so on the one hand, if you have a car, for example, on this on a parking lot in one image, and this is gone in the next image over time, then you can easily detect this change in the radar image. But even if the phase information gives you additional information, so for example, take a sandy area and a car has passed over the sandy area between two acquisitions, then you see the track of the car in the resulting change detection product. You will not see any changes with respect to the reflection. Also, you will not see any changes with respect to the area if you look at an optical image. But if you take the phase information, so the part of the wave which has been reflected on the ground, then you see that there has been a change, and then you can use this to identify, for example, tracks. Or on the right-hand side of this slide, you also see different helicopters which have been placed there in different timestamps. And you could also see that one of the helicopters, the yellow helicopter in this image here, has been moved in between the two acquisitions, but it was present at both times. So there was probably some maintenance or some operations of this helicopter. So this could easily be detected also with the radar images. You will not detect this just looking at the images without the phase information, or also using the optical image. Some other examples are here for the change detection based on, one example here from the glacier area in Chile, acquired with 3-meter resolution image strip map data, and the different colors show the different timestamps when the reflection was there. Let's say the most part of the reflection was there. Red for the December reflection, then there was green in the mid-September, and then also the early September. So 3 images combined, and depending on the different color, you see how these things changed over time. And I will do a zoom into this area here, where you see that if you look at the lower part, for example, you see that the change in the glacier was pretty strong in this period. And also in the water itself, you see different ice patches which have been there in specific times, but not all over the period when the images have been acquired. Another example of the movement of the glacier over time, which is also nicely visible using the change detection. So all these more grayish parts are areas where there hasn't been any change. All the colorized areas are areas where there has been a change over time. And also another example from the Soufrière volcano eruption in 2021 in St. Vincent and Grenadines. And you see that the red part in this image shows the lava flow, which actually reached down to the ocean here. And the green parts are areas which have been erupted or have been eroded based on the eruption of the volcano. And these are images, yeah, one from before the event and one from after the event. So the event was on 9th of April 2021. The images have been from March 31st and April 11th. The next main topic I want to touch is the interferometric movement monitoring. So you could do monitoring over time of the surface to identify changes over time with respect to, let's say, millimeter movement of the surface, which is also important, for example, for volcanic activities or other activities on the ground. And I will show you some examples. This example shows an image from the building of the train station in Berlin, in Germany. And you see that over time, there is a movement of this building with respect to the different seasons. So in summertime, as this is a steel construction, in summertime, the building moves compared to the winter time when the steel is cold. And this is visible by the colorized image here. And you see that, let's say, the surrounding is pretty stable over time, but this building itself, due to the steel construction, changes over time, and this could be monitored from space using the radar data. And this, as mentioned before, is based on the phase information. So this is the phase information shown from the satellite. And if there is a change on the surface, you see that different parts of the phase get reflected on the ground. And this is the exact information which can be extracted using this interferometric processing. And the changes which could be detected are in the range of 1 to 3 millimeters. You always need a base stack to start the processing, which is typically around 16 images. And then you could do the monitoring over time. You have to take some changes into account, like the influence based on the weather. But in general, you're in the range of 1 to 3 millimeters based on our data to get the information out of it. There is one example I want to show you from the Mosul area. The Mosul Dam, I need to change to and this. So this video shows the change over time, which has been monitored using the TerraSat data. And the movement which is shown here is in a range of plus minus 15 millimeters per year. So I think this is a pretty impressive technique to monitor these changes over time in the range of millimeters from space. And let's go to this next. The next topic I want to show are the very precise XYZ information which you can extract based on the radar data. Just a quick view on this. Based on 3 images, at least 3 images, you can do an automatic processing of the data, and on a point base, especially for very nice scatterers like street lamps, like man-made structures, you can detect or you can extract the 3D information in a range of 10 centimeters. So these are the ground control points, and this is due to the reason that we have the very precise orbit information from the satellite. So the last topic I want to touch is the elevation data, and which are also mainly based here in this example on the radar data. So we also have other elevation data in our portfolio in the range of 1 meter, 4 meter, 8 meter, and so on. But we are talking here about the global coverage based on the TerraSAR-X and TANDEM-X satellite in the range of 12 meter grid spacing with the World DAM. And with the update we've recently launched with the product, it's up to 5 meter resolution from pole to pole, with global access to the data as a surface model. And we are also working on getting the terrain data out of the data with some manual interaction, some manual processing of the data. This shows actually how both satellites are flying together, TerraSAR-X, TANDEM-X, flying in a close formation in a range of only several hundred meters apart. They're flying around the globe together. One satellite is acquiring, or one satellite is sending the signal, both satellites are receiving the signal, and this allows to do the processing of the elevation data. This is how the acquisitions look like. One satellite is sending the signals, both are receiving the signals, and this allows the very precise 3D data extraction. This is one of the first elevation data set which has been produced. So that's Iceland, and I think that's a result from probably around 2011, 2012, something like this. With the 12 meter resolution DAM global coverage, this was the product which has been launched in 2014, 2015. And now we made an update also with new acquisitions for the for the World DAM Neo, which provides a 5 meter resolution DAM. So increased resolution and also new acquisitions which have been done. And this gives a global access with 5 meter resolution, accuracy of 2 and 4 meter relative accuracy, depending on the terrain, acquisitions between 2017 to 2021. So actually brand new data, and with a global absolute accuracy of 2.5 meters from pole to pole. And this already gives, brings me to the end of the presentation with the general overview of our EO satellite fleet from Airbus with the different applications. And I think some of the applications are also interesting for the regions where you work in. And what I did not mention so far, additionally to the commercial exploitation of the data, we also have the TerraSAR-X, TANDEM-X, as this is a public-private partnership with the German Aerospace Center. We have access to the data via the science community. So you can go to the page of the German Aerospace Center and go to the science mission, and there get data, access to the data based on proposals which you can send towards the agency. Yeah, that's the quick overview. Sorry for the let's say time constraints which we had also with respect to the technical issues, but I hope that you had some good takeaways, and if there are 1 or 2 questions, feel free to shoot them.